Those of you that I know never look at the calendar. Your exam is Friday. Again, that will be over chapters 6, 7, 10, and 35. The same rules and game plan and style and format and blah, blah, blah as the first exam. You also will have the opportunity to retake it if you're here in class taking it in the first place. So it'll be available to you after class Friday, because that's when the exam's over. And you will have until Sunday night to finish it. So 2.5 days. But next week's fall break. So lest you think, oh, I have a whole week to take it. No, I'm just giving you 2 days to knock that one out before you forget about it. Homework 35 on chapter 35, relativity, is due tonight, so that you can see the answer keys tomorrow for studying. On that vein, remember, you can go back and see the answer key with my additional explanations to each question for all the past homeworks. When we come back, we will start chapter 13, after fall break, that is. Chapter 13 on fluids. How air and gases and liquids are fluids because they flow. So we'll start with chapter 13. There will be a pre-lecture on that one that'll be opened up after Friday. But you'll have a week in between to forget about that. That's why I'm helping remind you. And a little longer term, but the Friday after we get back, so in about 2 weeks, your superhero paper idea submission is due. You have to come up with an idea by then to get 5 points of your paper. Now, I won't lie. If for some reason after this idea you decide to change your mind, you can tell me about it and we can work out something. But this is to encourage you to be thinking about it so your paper will be better. The criteria are on the WebAssign assignment, so you can see what you need. You need the main fundamental physics principle you're going to use, like Newton's third law, or the second law of thermodynamics, or special theory of relativity, or whatever. Again, it doesn't have to be something we've actually covered in class. You need, there are 3 things. They're all listed there. But another one that people forget are works cited. You will need to show your resources for this paper. You don't need an exhaustive list at this point. I want to see that you've gone somewhere and you have a place you can go to get the information you need to write this paper, so that you don't spend all your time thinking about a certain topic, but when it comes time to going and getting info, you can't find any. I don't want that to happen to you. Again, you're not fixed with these. I just want to see you have something that you report. In other words, those could change by the time you turn in your final draft. But so that's going to be due in about 2 weeks. Questions on that stuff? All right. No, this is not clickers yet. This relativity stuff, just kind of wrap it up. So, because this is confusing for people, whether they admit it or not. And several of you have admitted it to me. So, let's kind of solidify some of this last material we went over. So, it's based on 2 postulates. One, Einstein essentially says that physics is the same. All this physics that I've been teaching you applies to everybody in certain reference frames. What are those reference frames? What's the criteria for those reference frames? Inertial, as opposed to non-inertial. And what's the difference? One's what? They can both be moving. But how is that motion? Describe the motion. If you're moving close to the speed of light, we say it's relativistic, and we have to start applying this stuff. But the difference between our reference frames, I showed it to you in that opening example. The book has a wonderful section on it in chapter 35. Inertial means the laws of inertia handle. That's all these laws we're used to and that make intuitive sense. But it means you're moving at a constant velocity. That velocity could be 0, but that's staying constant. Non-inertial reference frames are when that frame is accelerating. Remember in the picture they dropped the ball with the cart moving? Kind of like we had a cart that shot a ball while it was moving. If the cart was accelerating, it's in a non-inertial reference frame. And the theory of relativity doesn't apply to that. Because you're changing your velocity. So, point is, that second postulate says, yeah, the laws of physics all hold like inertia that were in inertial reference frames. Frames of reference where the velocity is constant. Given that, the consequences we saw were simultaneity. Events that happen at the same time right here, snap both my fingers at the same time. If you're cruising on a spaceship now going at relativistic speeds, at some constant velocity, say 50% the speed of light, do you see me snapping my fingers at the same time? What's that? Yeah, there's a difference in reference frame. So would the person on the spaceship see me doing it at the same time? Yeah, the general answer is not necessarily. In this case, no. Because they're in a frame of reference. There's relative motion between us. The difference in speed between us is 50% the speed of light. If I'm at rest, 50% speed of light, there's the relative motion. So yeah, each of us will see each other's events happening at different times. If you hop on the spaceship and go like this, what do you see on the spaceship? Simultaneous. What do we see here at rest with respect to the spaceship? Time slows down, time dilation. Lengths contract, their lengths seem to be shorter. And the events could be at different times. What if what from the ship's perspective, looking back at us, what does he see for my time, our time? Does our time look different than his? Yeah. Does he see our time ticking away more slowly or more quickly? Oh, yeah, sure. The key here is because it can get confusing between, wait, am I this person moving or this person moving? So that's why I'm trying to generalize here. If there's relative motion between the two reference frames, it doesn't matter who's moving. If you're at rest and I'm moving at relativistic speeds, then there's relative motion between us. I can be at rest and you can be moving. From my perspective, if I move away from you at 50% the speed of light, from my perspective, in my reference frame, everything's at rest with respect to me. It's you that are moving that way at 50% the speed of light. Does that make sense? It's a matter of perspective. That's why all motion's relative. We could both be moving. As long as there's motion between us, we're in different reference frames, and all this stuff applies. Time dilates or slows down. So, I would see your time as ticking away more slowly. You would also see my time as ticking away more slowly. Remember the paradox? We both think each other are aging more slowly. We would also think each person's meter sticks are shorter. If I'm looking at yours, I would think yours is shorter than my meter stick. And you would think mine's shorter than your meter stick, because there's motion between us. So it's time dilates. It always seems to slow down for the other person. What do you what do you notice in your frame? Anything peculiar? One vote for no. In your frame. Does it matter whether your frame's moving or not? No. So we can, as long as you're at rest with respect to stuff in your frame. So right now, we're all at rest. We're all at rest with respect to each other. Everything seems normal. Normal time, normal distances. We get a meter. Now we all hop on a spaceship together. We're at rest with respect to each other still. So no difference. Basically, relativity is always about the other guy. For you, everything seems normal. So I wanted to I pulled this up to replay this animation. So the top is the spaceship's frame of reference. So that's like you're with the spaceship, riding along with it. And the Earth's frame of reference, looking at the spaceship. So you can see here the times are different. In the frame of reference of the spaceship, you time it to go up and down. Your clock just ticked off 4 nanoseconds. If you're in that frame. But if there's motion relative between the two frames, you're back on Earth in a different frame of reference, you see that same event taking 9.2 nanoseconds. See how it took longer? It seems like time slowed down and it had more time to do the same event. Does that make sense? Flip this around. Let's now do the light clock on Earth. And the astronaut is looking at ours. What time will the astronaut think it takes to go up and down? Looking at us back on Earth. If we did the experiment on Earth. 9. Because the astronaut sees my time dilate or slow down. It is always slowed. And likewise, distances. I didn't show this one. If you're going 50% the speed of light, then if you're in the ship's frame of reference up here, again, no difference. You don't see any length contraction. You're in that frame. But if you're in Earth's frame of reference looking at the ship, see how you see the ship? It looks shorter. Here we can pause. It's contracted in the length it's moving, the direction it's moving. If you go even faster, 90% the speed of light, then from Earth, the ship looks even shorter in the direction it's moving. Notice it didn't shrink vertically. It's not moving in that away from you vertically. It's the way it's pointed. Likewise, if you're on the ship looking back at the Earth is receding from you at 90% the speed of light. What do you notice about the size of the Earth? It gets squashed too from your perspective, your frame of reference. Again, both are right, but both see a length contraction. And times dilate. If one changes, the other has to. They're tied together. Space and time. Space-time. They're just two aspects of the same thing. Like mass and energy are two aspects of the same thing, related by the velocity of light squared. Questions? Comments? Yeah.
So if we're like looking at like planets and stuff, can we tell like how fast they're moving by like stars and stuff? If they are like squished, or is there astronomical things that we can like measure by them?
That's a good question. Is there anything astronomical we can notice and measure that? Probably. See if I can think of any at the moment. Times? Well, we saw it sufficiently enough, like putting a clock in an airplane and whizzing around. We noticed that. Our technology was sensitive enough to detect the very, very, very small change. There's one. One of the first tests of this was muons. They're cosmic rays. these small particles that come from space. Something happens out there and they come into our planet. Or they can happen in the upper atmosphere. If they make it down to the Earth, we can detect them. Well, they have a half-life. You've probably heard of half-life. Things decay. Basically, they don't disintegrate. They just turn into something else. You could have something and then all of a sudden it decays, which means it turns into something else. It's no longer what it was. Muons have a certain half-life. We know what that is. We measure it here in the lab at rest. It's in the same reference frame. On average, over time, it takes yay long for them to decay. It's half-life. We know that. So some scientists took them up to the top of a tall mountain. Well, they're coming down from the upper atmosphere. So they measured, they tried to detect them up high where they had less time to come down, to have an idea of how many were up there. They did the same thing down at the bottom of the mountain. They knew the height of the mountain, the distance. If that's how far it is, and it takes yay long for them to decay, if they're falling with gravity or have a certain velocity, they know how long it should take to get from here to here. They compared that with the half-life, which was longer. They should be hitting the ground. No, the other way around. It's shorter. The time it takes going at their speeds to cover that distance of the height of the mountain should take longer than they decay. They should all, on average, decay before they make it to the ground. Are you with me so far? They should all decay and never make it to the ground, comparing the number they detect. What they noticed was when they came to the ground and detected it, they detected way more than should have ever made it. Why? Theory of relativity. They are cruising at relativistic speeds. So nothing seems different to them. Two ways to look at it now. We see their lengths as contracting when you're going that fast. So to them, from our perspective, they have less distance to cover. So they can make it. And they do. Looking at the space. Look at it with time. From our perspective, they're moving relative to us. Their time slows down. It's as if they got more time to make it. So relativity explained it. And that was one of the first visual observations of this. There's one. By a show of hands, who has read or watched Ender's Game? Not the majority, but quite a few of you. Now, spoiler alert, I won't lie, I don't give away the whole plot thing or whatever, but one thing, they do keep a secret for most of the movie, so if you don't want to know, I don't know, close your ears for a moment. But, the gist is, and I'm summing it up, here's this guy that figured out how to beat some aliens. Well, here's a new guy that's in charge of beating the aliens. They need to keep doing it. He's a commander, and he hooked the two up. Well, the new good guy that's supposed to win and the old guy that figured out how to win got together. And the new guy asked, "Why aren't you dead?" Ender asked him, the new guy. "You fought your battle 70 years ago. I don't think you're even 60 years old." I think you can see where I'm going with this. There's something to do with relativity. And that's what the old guy says. The miracles of relativity. They kept me here for 20 years after the battle that he won, even though I begged them to let me to command, blah, 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 blah. So they sent you out in a starship and got you up to a relativistic speed. And he interrupts him, the old guy, and says, "Yeah, then I turned around and came home. It was a very dull voyage, Ender. 50 years in space the old guy spent. Officially, only 8 years passed for me. Because remember, he's in the spaceship. He's in that frame of reference. Things seemed fine to him. Right? So it's officially, he's in quote, only 8 years passed. But he said, no, he was out there for 50 years. There's some time dilation going on. But of course, it felt like 500 for him. All of this, here's the spoiler alert, they did this so that he could survive until they had enough technology to beat the aliens. Now the old guy could pass his knowledge on to the new guy, and hopefully they could win. I'll let you watch the end of the movie to see if they do, but you know. So the idea here is you got a difference in time. One seemed to think 50 years passed. The new guy, us here at rest on the earth, 50 years clicked away. We thought he was off in space. We kept him in a spaceship for 50 years at relativistic speeds. Because of this relative motion, from our perspective, his time ticked more slowly. Remember the twin paradox? When they got back together, one of them's younger? He's younger, that old guy. It was as if only 8 years passed. He only aged 8 years for the 50 years we saw him be gone. What's the ratio between 8 and 50? 50 divided by 8 is 6.25. That's the Lorentz factor. That gamma, the 1 over the square root of 1 minus the percent of the speed of light squared, the factor is 6.25. Given that, plug it in. I calculated this. I was curious. Okay, how fast did they have Maser going for 50 years? They built a spaceship to get him at a velocity at 98.7% the speed of light. Probably pretty impossible, but you know, it's in the future. So according to the theory of relativity, if you could go 98.7% the speed of light for 50 years, you'd only age 8 years. We could preserve you to come back and share your knowledge. That's what they did. I thought that was pretty cool. I mean, that was kind of the underlying reason of how that worked. So, oh yeah, okay. So I have the test in front of me. I'm going to look through it as I did before class and see, okay, what should I tell you? What should I emphasize? Do you have any major questions right now you want to ask? Things that are confusing to you? Because I've already told you a lot of this already, trying to review the relativity stuff. Your pulse. Pulse is essentially a timer. Think of it as a clock. So in terms of relativity, biologically, you know, your heart, dun dun, dun dun. With each pulse, it's as if time flows by. No, it's as if we flow through time. Boom, 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 boom. It's like watching the hands of a clock tick. Takes a second. Well, if there's motion relative between us, and I send you off at a spaceship going 98.7% the speed of light, then I see your clock ticking 6.25 times more slowly than mine. So for every one of my heartbeats, no, for every 6.25 of my heartbeats, dun dun, dun dun, dun dun, dun dun, dun dun, dun dun, dun, one of yours beat. That's why you age more slowly. Does that help?
In that same strain, it's the same question, but it's about volume.
Volume. Oh, that length contract, but only in the direction you're moving. So if there's relative motion between us, you know, like this, coming at us, then you'll see my length contract in this direction. You won't see it contract in this direction or this direction because there's no relative motion between us this way or this way. Like the ship. It got shorter, but it stayed the same width or height, if you will. Thus, that affects volume. As you go faster and faster, and again, it doesn't matter which reference frame, time slows down for the other guy. Not for you, but for the other guy. So as you go faster and faster, time slows down more and more and more. What if you could go the speed of light? What happens to the time for the other guy? It would stop. You keep slowing down, slowing down, slowing down. You know, if you could approach the speed of light, get there, it would stop. It's as if time stood still. You wouldn't age at all. And lengths would get shorter and shorter and shorter. There would be no length. There would be no distance to cover. everywhere would be right before you if you could go the speed of light. The theory says you can't get there, but that's the way to think of it. It's an asymptote that you approach. It's kind of fun. All right, we did a lot of collisions with momentum and energy. What's conserved in a collision? Total energy and total momentum. They're always conserved. Right. All right, so the total momentum before a collision has to be the total after. So say you had I gave you a collision like some of the homework did. That's why I give you those homework questions. Hint, hint, wink, wink, go study those. Let's make it up. Let's say you have a 5 kilogram piece of a ball and you throw it at another ball that's not moving. Let's say it's a kilogram and its velocity is 0. This velocity is, I don't know, 10 meters a second. You can see an impending collision. If they stick together, let's say it's clay, they stick together. What's the final velocity of the system? What do I do? Walk me through it. What's the underlying concept? I always start with a concept. How are we going to figure this out overall?
So it's like mass times velocity.
Mass times velocity.
Plus mass times velocity.
Yeah, the two. So what you're getting is total momentum is conserved. Here's the total momentum before. This guy's momentum is 0. So initially, it's all this. And what's his momentum? 50 units, kilograms, meters, second. So that's the total momentum before. What's it have to be after they collide and stick together? Yeah, it's got to be 50 over here too. How do we find its momentum? mv, right? It's the same. But they're together, so it's m plus m, and they're moving at the same velocity. That's got to equal 50, right? Because it was beforehand. Let's see, their masses I gave you were 5 plus 1, so 6. So 50 divided by 6, whatever that is, that's your velocity. That's how fast they'd be going afterwards. So we use total momentum to find such things when you have collisions. You could do the same thing with total energy. What if, though, the collision, if this is an inelastic collision because they stick, where does some of the kinetic energy go? Yeah, heat. So if you didn't catch this point yet through the homework and the text, kinetic energy is not always conserved. You could start with so much kinetic energy, 1/2 mv squared, this guy. That won't, these two together won't have that total amount. It'll get converted to some kinetic energy, and what else? Heat. It's a Q in physics, yeah. The work done by friction or the deformation, it'll turn to heat. Some of the energy went there. So you won't end up with the same kinetic energies you started with if there's deformation. If they bounce off each other, though, it's a perfectly elastic collision, then the kinetic energy should be conserved, ideally. When you have a collision, there's forces on the two objects, right? How do they compare? This one's bigger and it's moving faster, and it comes in and slams into the lighter one that's not moving. Who feels more force? Newton's third law. All forces come in pairs. They're in interaction. They have to be the same. Those of you that still want to say it's the lighter one, you're just thinking ahead to Newton's second law. It has a greater change in velocity, thus acceleration, because it has less inertia, less mass. But the force is the same. Who feels the force for more time? The big one? How come?
Is it an inelastic?
Yeah, in this case, they stick together. Should be the same. They're an interaction. When this one's in contact with this one's in contact for the same amount of time. So it has to be the same time of impact. Even if they bounce off each other, they're in contact with each other for the same amount of time. We did force times time. What's that called? Impulse. That brings about a change in momentum. If we ran a car into the wall, it comes in with some certain momentum and this stops it. It had a change in momentum. In order to bring about that change in momentum, the wall has to apply an impulse, a force for a given amount of time in that collision. Okay, replace the wall with a haystack. The haystack, let's say there's enough haystack there that eventually the car stops. How does the impulse change? Yeah, the impulse doesn't change. If it came in with the same momentum and it stops, it's the same change, same impulse, same product. But yeah, if it takes longer with the haystack, you don't need as much force, and so maybe you can survive. How about if something's falling? You have so much potential energy up here. When you drop it and it falls, what's it convert into? Kinetic. Right. What if you consider air resistance? Does anything change? Yeah, that potential energy still converts to kinetic. But what else does it convert to? Heat. So if you do this in a vacuum, the kinetic energy here should be the same as the potential here, right? Because its total energy is conserved. Now, though, if you do it in air, some of this energy also goes, as you just said correctly, to heat. So how much kinetic energy do you now have? Less. Does that make sense? We talked about kinetic energy and practical implication for all of you that like to go over the speed limit. Kinetic energy is 1/2 mv squared. V squared. So if you go twice as fast and you slam on the brakes, how much farther will it take you to stop you? It's force times distance. Yeah, how will that D compare if you're going twice as fast now? Yeah, it'll take 4 times as far to stop you because energy has to be conserved. The energy that's going to stop you is the work done by the brakes. So that work is converting your kinetic energy, changing it from something to zero. Just don't forget that squared factor. I asked you about that. Ooh, let's do this one. You had a question and I did a demo with a fan cart. If I turn this fan cart on and it blows air that way, it exerts a force on the air exerts a force on the cart, and it moves that way. And then remember we put a sail on it. It's just a different cart. So if I do the same thing, it's still getting propelled that way, but now the air is also blowing on the sail. Do that again. So it's pushing the cart that way at the same time it's recoiling, and it didn't move. Here's something interesting. This sail is curved. Can you see that? I'm going to put the curve facing the wind. They make something like this called a Pelton wheel. Pelton wheel. So now when the air hits this sail, it's going to get deflected and curve and swing back. It's like it bounces. Remember our happy sad balls where one bounced and one didn't? Watch this. Now it seems to have enough force to move that way. Why? Yeah, it has something to do with the air being redirected. So before we had the air pushing on the sail that way, and that wasn't enough to counter the recoil of the fan blowing in the first place. But this air that goes into the sail is doing what? Being bounced back. Is that going to take more or less impulse? If the air comes in and hits, it's like our car into the wall. It comes in with some momentum and the sail stops it. There's a change in momentum. Like the sad ball that doesn't bounce. But the happy ball, it had that change in momentum to stop it, and then another change in momentum to kick it back. So ideally, it's twice as much the change in momentum, twice the impulse, which means it's twice the force. So if you just get something to stop, you feel a force. But if you can exert enough force to stop it and kick it back, then you get that additional recoil, and it's enough just by making it curved so that it throws it back to push it that way. Yeah, there's twice as much force as there was before pushing the cart that way, to move the cart. Because the sail not only stops the air from moving this way by pushing it that way, it pushes twice as much that way and kicks it back. Does that make sense? These wheels, you can Google it. A Pelton wheel. Basically, they're curved. They're like cups. And they shoot water at them, or air, a fluid. And look what happens. If you shoot it in, instead of just hitting it and kind of, what's it going to do? It splits and kicks it back. Sprays it backwards. So it's essentially making the fluid bounce off of it, giving it more kick, more impulse, more force. What can simple machines not do? Yeah, they can't create more energy. Nothing can do that. I mean, total energy is always conserved. But they can do what? Yeah, they can change the force. You either need more or less, depending on which side you're on. Well, it has to compensate if you do that. Distance. Because the energy is the same. Work is force times distance. Work was force times distance. What was power? Joules over second. Those are the units for energy for time. So if you do energy and it takes a certain amount of time, you can now figure out the power that it took to make that happen. Yes, work transforms energy. So yeah, work, force times distance, is in units of energy. Absolutely. Do you remember efficiency of a simple machine? That's right. Efficiency was the energy out over the energy you put in. Whoops. So if you only get 50% of the energy out that you put in, we just say it's 50% efficient. Or you do something and say there's a collision by splatting the ball, and now there's less kinetic energy. It's like we put this kinetic energy in, but we end up with less. There's the output, there's the input, We could say this collision had a certain efficiency. Works the same. Yep. 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 Friendly reminder, you guys know how to find kinetic energy and momentum. And gravitational potential energy. Realize all of these rely on more than one thing. This depends on the mass and the velocity. So does kinetic energy, the mass and the velocity. Potential energy depends on the mass and its location. So in these questions, more than one thing can change. But here's your guides to thinking. You just reason them out. You know, if the mass doubles here, what else doubles? The momentum. Yeah. Well, so does kinetic energy if it's moving, right? That idea. We shot things, projectile motion. You guys all got by now, I know. You drop two things at the same time, they hit the ground at the same time. What if I throw this one horizontally? Same time. What if I threw this one down at the same time I just dropped this one? The one throwing will hit first, yeah, because it's going to get there faster. It has an initial vertical velocity, which means it also has an initial vertical momentum. It's got more kinetic energy in the vertical direction initially than the one you just dropped. So of course it'll get there faster. Good. When can you use the formulas for Newton's laws? What speeds? Yes, slow speeds. Yeah, less, not going fast. When can you use relativity equations? Right, all of them. We just don't need to at slow speeds, but they work. It's like Newton's laws are an approximation for the slow stuff. Yeah. Did that. Any other questions for you? If not, I got a couple clicker questions to help with this relativity stuff since it's a little more confusing. Anything else? Well, ask these real fast and see. All right, polling's open. There's your info. And I just asked you this question earlier this lecture. See if you remember. I re-asked this one mainly to emphasize Einstein has two theories, the theory of special relativity and the theory of general relativity. General relativity has to do with one type of reference frame. Special theory of relativity only works for the other kind. How's logging in going? 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Most of you thought D? That's right. Sure. So the laws of physics are the same for everybody, but only for certain reference frames. What are those reference frames? Inertial, which means what? Constant velocity. If you're accelerating, all bets are off for the special theory of relativity. Does that help? Okay, we covered this one too. Sometimes, you know, it takes being exposed to it more than once before it sinks in. So you got two different reference frames. We're talking about simultaneity here. What's that?
Like any kind of reference frames, or
Two reference frames. That's all they tell you. You're hinting at some. They could be have the same, be moving together, or have motion relative between them. It didn't say they necessarily which. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. 81% saying may or may not. Correct. If the reference frames are going, there's no relative motion between them, then they will agree on the events. But if there's relative motion between those two reference frames, they won't agree. One more. This one. All right. You're inside the rocket ship going fast. What would you notice about your companions that are also inside the ship? We covered this also. This is good. We'll have time for this, and then I can do one little demo to send you off. It's quick. Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Meh. Most of you, that's right. You don't notice any difference in your reference frame. It's always about the other guy. All right. Drop these balls, they go to a certain height. It's not the same height. Why? This does not return to its same height. This does not return to its same height. Potential energy is converted to heat and when this squishes in deformation. So it doesn't all come back as potential. Exactly. Some energy is converted to the floor and the energy it takes to squish this. Sound and heat. Yep. Some energy is lost to air resistance too. So that was, if there was no gravity, they wouldn't fall. Watch how high this one bounces. All right, now, watch how high this bounces. Don't watch this, but watch how high this bounces. Even less. Where did that energy go? Right. So, we can do the same thing with an egg. What'll happen? Here's a collision. Will it break? It depends on the time of impact, doesn't it? Is this squishy? Is it squishy enough? Ready? See you Friday.